In this video, we're going to be looking at how to monitor machine learning models with Evidently. Evidently is an MLOps tool designed to help in the evaluation, testing, and monitoring of data and AI-powered systems. What's in this video? Well, firstly, we'll be covering why we need monitoring in our machine learning systems. And then secondly, we'll cover how to use Evidently, which includes a code walkthrough. Why do we need monitoring in our machine learning systems? To answer that question, we first need to make sure we understand exactly what machine learning is. Machine learning enables machines to perform tasks without being explicitly programmed. Instead, they learn how to perform these tasks by learning from patterns within data. Let's take this population of circles to illustrate exactly what we mean. Here we have green circles and we have grey circles. The location of the circle in the box represents the features of the circle. Two circles close together have similar features, while two circles with very different features are far apart in the box. But say in the future a new circle appears. Could we use the features of that circle to predict its color? The answer is yes. We can use machine learning to train a model to perform the task of classifying the circle for us. But what is training? Training is the process of the machine learning from the patterns in the data. And we will try different solutions, and the goal is to end up with the red line, which is our best solution that automates the classification of the circle based on its features. So in this example, all future circles that fall below the red line will be classified as green. All circles that appear above the red line will be classified as grey. Evaluating on the training data, we can see the performance isn't too bad. We get one classification wrong here. So, as a summary, what is machine learning? It's when machines learn patterns from the training data to perform a task. And the objective is to make accurate predictions on new unseen data. But crucially, the performance of the model depends on how similar the patterns and distributions in the unseen data is to that of the training data. What happens if the distribution of our unseen data is different to that of our training data? Well, then we experience model decay. Model decay is the deterioration of a model's performance due to changes in data patterns. So for example, we have a model in time interval 1, which is immediately after training, and the classification accuracy is 99.2%. But then in some period, time interval 2, say 6 months after training has taken place, the accuracy falls to 70.8%. This is defined as model decay. And one of the primary causes of model decay is drift. The first type of drift we're going to look at is data drift. Data drift refers to a change in the distribution of an input value or input values. So for example, we have a distribution of weights in a population in time interval 1. But then in time interval 2, the mean value for weights increase and the variance reduces. This is defined as data drift. So data drift refers to a change in the frequency or distribution of inputs. This pushes the model into an unfamiliar feature space and results in poorer performance. The second type of drift we're going to look at is concept drift. Concept drift refers to a change in the relationship between inputs and their respective outputs. So if we refer back to our population of circles, here we had a decision boundary that automates the classification of the color of a circle based on its location within the box. Here we can see the line works pretty well because most circles below the red line are white and all circles above the red line are grey. But in time interval 2, we can see this relationship no longer holds as we've got grey circles below and white circles above. This is defined as concept drift. So concept drift is defined as when the relationship between inputs and outputs change. The model starts making wrong predictions because old patterns no longer apply. And this is why we need monitoring. Monitoring is needed because models assume that future data looks like the training data. But in real life, data shifts and then performance drops. And monitoring helps us detect when this happens so we can retrain our model on more relevant data. So now let's dive into how we use Evidently to monitor our machine learning systems. Evidently is a tool used for evaluating, testing, and monitoring machine learning systems. It helps us to detect things like data drift, concept drift, and other quality issues. And the objective is to use Evidently to flag when these issues start arising so we can reduce the impact of model decay. So to monitor, we've already established we need data from 2 distinct time intervals. As our model isn't in production, we have to simulate production conditions. And we'll do that by creating 2 different datasets representing 2 time intervals. The first time interval will be represented by our training data, which will be our penguins dataset from Seaborn. This dataset has features and it has ground truth labels that are used to train a model. Our reference dataset will be our gold standard. So we want it to have 100% accuracy. And so to achieve this, we will simply duplicate the ground truth column and label it as the classification column, and therefore in time interval 1, our system will have 100% accuracy. But for time interval 2, we want to make things interesting. So what we'll do is we'll take the features from our training dataset and apply data drift to the features. We'll then feed these features to the model and generate classifications, and then we'll simulate the behavior of a labeling team by creating ground truth labels. And the ground truth labels will determine the performance of the system in time interval 2. So we generate the 2 datasets for the different time intervals using Python code. But in our walkthrough, we'll be focusing on the portion of code that's relevant to Evidently. So if you're interested in seeing how we implement the system in this diagram to generate the 2 time intervals of data, then you can click the link in the description and that will take you through to a GitHub repository that contains the code for the system in its entirety. So let's dive deeper into Evidently. To use Evidently for monitoring, we need to wrap our datasets from our 2 time intervals in a way that's easy for Evidently to use. So an Evidently dataset is an Evidently friendly wrapper for your data. And within our Evidently dataset, we define a schema using the data definition class. Within the data definition class, we define which columns are categorical, which columns are numerical, our ground truth and classification columns, and we also tell Evidently whether our task is a multi-class classification task, binary classification task, or a regression task. So here we have the create datasets functions that we have defined in our project. And in this function, we're going to define our Evidently datasets. So the first thing we're going to do is define the schema, which essentially gives evidently all the information it needs about the columns within our data sets. So the first thing is we use the data definition class to list our numerical columns within the dataset and our categorical columns. Then we use the classification parameter and the multi-class classification class to tell evidently that our task is a multi-class classification task, and we specify our target and prediction columns. In our dataset, the labels are ground truth and classification. Next, we read our training data in, and that will be the data for time interval 1. That returns a data frame, and we do some manipulation to the data frame to get the labels in the right format. Then we use a function that I've defined earlier, and you can see this function in the GitHub repository, and we return a data frame for time interval 2. Then we use the evidently class and method from pandas to wrap our data frames and use the data definition parameter with our schema to create an evidently dataset that wraps our data frames and assigns a schema so that evidently can understand exactly what's in our dataset. So we do that for dataset from time interval 1 and dataset from time interval 2, and the function returns our evidently datasets for both time intervals. Let's commit that to memory and execute the code. And we have the datasets created. The next evidently concept we need to understand is evaluations. Evaluations are made up of two components. They're either metrics, which are single descriptive statistics, for example, the count of columns or the mean value for a column. Or the second type of evaluation you can have is a test. A test provides a pass or fail result for a specific condition. So if you test for drift, you can get a pass or a fail, or if you test for empty rows in your dataset, you can get a pass or fail result. So for metrics, you can calculate metrics for columns or datasets. And likewise, those corresponding metrics can be used as tests for columns or tests for datasets. So now we're going to construct an evaluation that consists of column level metrics only, and we'll do that using our column level evaluation function. This takes in our two datasets. So to construct an evaluation, we use the report constructor. And within that report constructor, we pass a list of metric objects. These metric objects are evaluations, and the column level metrics require the column level parameter to tell evidently which column to perform the evaluation on. So here we're running the median value evaluation on 4 columns and the unique value count evaluation on 2 columns. Let's head over to the evidently documentation to see what these evaluations do. So here we have the median value evaluation. You can see it's a column level evaluation that computes the median value of a given numerical column. Heading over to the unique value count metric, you can see again it's a column level metric that counts the number and share of unique values. Moving back to the code, we assign our report to the column evaluation variable, then use the run method on the column evaluation variable to perform our evaluation. And this takes in our two datasets. And the important thing here is to note that our current dataset must be first in the run method and the reference dataset second. This produces our results, and then our function returns these results. Now, if we express our results as the last expression in a Jupyter Notebook cell, then we'll render the results in HTML form. So as we can see here, we have the median value evaluation conducted 4 times, and then the unique value count evaluation conducted 2 times. Let's examine the first report, the median value evaluation on the bill length column. You can see that the current median value is 51.5 and the value for the reference dataset is 44.5. So you can see that the median value has increased after we have applied drift to our data. So now we're going to look at constructing an evaluation that consists of dataset level metrics. So we will do that with our dataset level evaluation function that takes in our 2 evidently datasets. Then again, we'll use the report constructor and pass a list of now dataset level metric objects. Here we're using row count, column count, empty columns count, and empty rows count, and they're pretty self-explanatory. They perform these evaluations on our entire dataset. So we assign our report to the data set evaluation variable, and then we use the run method on that variable, passing our current dataset and our reference dataset in that order. Then our function returns the evaluation results again. Now, if we call our dataset evaluation function, passing our 2 datasets with the current dataset first, that will return the evaluation results, and then if we use the evaluation results as the last expression in the cell, this will render the HTML version of our results. So if we scroll down here, we can see our results. We've got the row count for the current and reference dataset. We've got the column count for the current and reference dataset. We've got the count of empty columns for the current and reference datasets, and a count of empty rows for both datasets. Next, we're going to use our column evaluation with tests function to construct an evaluation with tests. The first thing to recall is that tests are evaluations that have a pass or fail outcome. And the pass or fail outcome is determined by the threshold conditions for the test. In Evidently, you have 2 ways of setting threshold conditions for our tests. One way is to use Evidently's default threshold conditions, and the second option is to use custom threshold conditions that we can set ourselves. So first, let's look at how to construct a test using Evidently's default threshold condition. To do that, we set up an evaluation again using the report constructor, and we pass a list of our metric objects that we want to use. Here we're using the median value metric object again, and we're performing the evaluation on the bill length column. The first thing to note is that a metric object also has a corresponding test, and if we want to use the tests within the metric objects using default threshold conditions set by Evidently, then within the report constructor we set the parameter include tests to equal true. Now let's head over to the documentation to see the details of the default threshold condition. So here we have the median value metric object, and here we have the details for the default threshold conditions for the corresponding test for this metric object. So remember, we're performing tests in relation to our reference dataset. So we're comparing the values of our current dataset to that of our reference dataset. And therefore, with the Evidently default threshold condition, the test will fail if the median value for our current dataset differs by more than 10% when compared to our reference dataset. So that's how to construct an evaluation that includes tests using Evidently's default threshold conditions. Next, we're going to look at how we can configure our own custom threshold conditions. Well, to do so, we again use the report constructor and we pass a list of our metric objects. As standard, we use the column parameter to define the column which we want to perform the evaluation on if we're using a column level metric. Then within the metric object, we use the tests parameter and we include a list with the following expression. Now let's break down each component of this expression. We have the condition here, which is GTE, and we have the threshold, which is determined by the reference constructor from evidently. The reference constructor must be used for tests that have a reference. And that's what we're doing. We're running tests that compare our current data to our reference data. Within the reference constructor, you can determine whether your threshold is a relative threshold, i.e. determined by a percentage difference, or an absolute figure. Here, we're choosing a relative threshold, and we're setting that equal to 0.01, which is equal to 1%. So our threshold is comparing our current dataset to the reference dataset by 1%. Then we defined the condition GTE, which equals greater than or equal to. So this expression means our test will pass if the median of our current dataset is at least 1% bigger than the median of our reference dataset. So again, to perform the evaluation, we use the run method and pass our evidently datasets, and our function returns the results. Now we call the functions and render the results for our first test. Now here we can see we've calculated the current median and the reference median, and we have the metrics as standard. But now we also have a tab called tests, and we can see that the test has failed. Remember, this is for our default threshold condition. Now we can render the results for our test with custom threshold conditions. So we can go to the test and you can see it's passed. And it passed because we set it to pass if our current median is more than 1% bigger than our reference median. But we already know it's more than 10% bigger. So this test has passed. Now we're going to look at how we can monitor our machine learning systems and detect drift and other performance issues. We'll do that using our function preset evaluations. And again, we pass our current dataset and our reference dataset. One way to perform evaluations is to use evidently's preset evaluations. These are groups of evaluations that are compiled for a specific purpose. So here you can see we have the data drift preset and the classification preset. The data drift preset combines a number of evaluations designed to detect drift within a machine learning system. And the classifications preset is a combination of metrics and tests that are designed to evaluate the performance of a machine learning system that's task is a classification task. We use the report constructor, pass a list of the metrics or presets in this case, and to use the default evidently threshold conditions, we set include test to true. We again run the preset evaluation object, and that returns our results, and our function returns the results. Again, we can call the function that will run the report, and you can see here we have a number of metrics, and you can see the count of columns that have drift, and you can see for 2 columns there's drift is not detected, and for a number of columns we have drift detected, and this is because we applied drift in our code to simulate production conditions. We can also see that we have a test tab, so we can see we have a number of tests. 6 have passed, 7 have failed. The last thing to cover is evidently results. So in this tutorial, we have chosen to render our results in HTML format, but there may be cases where you want to produce results in a different format, and evidently accommodates this. So you have two further options, which is to render your results in the JSON format or a Python dictionary. So here, this shows exactly what you need to do. You can call the JSON method on your results, and this will produce your metrics in JSON format, or you can use the Python dictionary method, and that will produce your results in a Python dictionary. So that's it. We've covered in this video why we need to monitor machine learning systems and how we can use evidently to monitor for things like data drift. If you found this video useful, please subscribe so you get notifications when we release future tutorials.